Here is our first talk. This is Rebecca Atkinson with mitigating sampling errors using optimal localization in Ensemble data assimilation.
Hi everyone. I'm Rebecca Atkinson and I'm a PhD student at the University of Surrey. And before I start, I'd just like to acknowledge and thank my supervisors, Ian Rulstone and Sue Hughes at the University of Surrey and Jonathan Flaherty at the Met Office for their support and guidance with this work. I'll give a quick overview of the talk. I'll give a very brief background on localization. I'm going to present 3 types of optimal localization, a model setup in which I perform ideal experiments comparing optimal localizations in a traditional form. I'll give some numerical results and conclusions, and finally, future work I intend to do. Very briefly, localization is widely used in ensemble data assimilation to address sampling error occurring in the covariances. And then perhaps the most common form is Gaspari cone localization, which is similar in shape to the Gaussian but has compact support. It has a width that must be tuned based on past data, and that tuning process is quite ad hoc. It's used quite widely because it's known to be been shown to be a convenient process that works quite well in most applications. However, it's not in any way a theoretically optimal shape. So this piece of work is interested in investigating the optimal localization that optimizes the analysis produced by data assimilation. So in order to derive optimal localizations, I first simplify the problem by assuming single point observations. So in the Kalman filter formulation, this means the gain simplifies to this form, the sparse gain. And then we can derive a series of optimal localizations with different forms based on assumptions about what's known about the covariance matrix and how the localization is applied. So in the first case, we assume that there's a single true covariance matrix. I call this OSTC, for a single true covariance matrix, and apply the localization directly to the sample gain. In most cases, there isn't a single known covariance matrix, and if anything, the reason ensembles are used is because we can't know the true covariance matrix in detail. So a second form is optimal for a variable true covariance matrix, where it's assumed there's some statistics can be known about the distribution of possible covariance matrices. And again, the localization is applied directly to the sample gain. In a third and final form, it's again assumed there's a distribution of possible covariance matrices. This time, a localization is applied to the difference between the sample and mean gain, which has the impact of damping. The localization then damps towards a mean as opposed to towards 0. The reason for this is because it's known that localization can introduce additional imbalance into the analysis, and it's expected that damping towards a mean as opposed to 0 will reduce this effect. So in each case, an optimal localization is derived by first defining a cost function in terms of the difference between a localized sample gain and the mean gain, and then minimizing it. So in this right-hand column, the resultant localizations are shown. In the first case, OSTC, the optimal localization is given in terms of a true gain, which is obviously, again, not useful, because if the truth is known, we wouldn't be using an ensemble and we wouldn't need localization. However, it's still expected that some improvements may be seen if we used a mean gain and treated it as a true gain in this form. But it's expected that OVTC and hybrid forms will be an even greater improvement on that. And they're given in terms of a mean and variance of the true, an expected mean and variance of the true gain, and a mean variance in the sample gain. So I've just described 3 optimal localizations of the gain. However, in this work, they're not going. They'll be applied to the covariance, not to the gain. There's a number of reasons for this. Firstly, there's an equivalence between application to the gain and the covariance, under the assumptions that there's a single observation being assimilated, and the variance in the sample variance, and also in the variance across the climatology, is negligible. The choice has been made to optimize the gain because the aim is to get the best analysis and not the best covariance. However, the sampling error does occur in the covariance, so it's expected to get better results, particularly if assimilating multiple observations, if we localize the covariance and therefore the error at its source. Having defined a series of optimal localizations, the next step is to we needed a ideal model in which we can generate all the relevant statistics and test the application of these localizations. We started with a toy balance model that's been previously used by Graeber et al., which is based on the shallow water momentum equations and geostrophic balance. And essentially the states are balanced wave solutions for height and wind on a one-dimensional domain. And the states and statistics can be defined by defining distributions for the amplitude of the height, the wave number, and the phase shift. So I'll show one set of results for a regime, and in this one, the wavelength, the mean wavelength and mean phase shift are chosen from a climatological on a climatological level, and from uniform distributions, and there's a scenario or ensemble sampling process which then selects the amplitude and the height from a uniform distribution, and the wavelength and phase shift from uniform distribution centered on the means found from the climatology. So to give an example of the states, this produces, this is showing the height on the left and the wind states on the right across the domain. The second plot shows 2 ensembles, one in blue and one in red, and it can be seen that there's a lot of error in the ensemble, a lot of uncertainty across most of the domain, except for in a small range around the phase shift, so around 4,000 for the blue and around 0 for the red, where all the ensemble members agree. So there's a peak in the height and a crossing through 0 in the wind. So now I can show the optimal localizations that are produced from this regime. And I'm showing them alongside a Gaussian, which has been tuned for assimilating a single observation of the height on the center of the domain. And to make it easier to compare, this plot showing a slice through the center of each quadrant of each covariance matrix, or each localization matrix. So a number of things are worth pointing out here. The Gaussian localization has been tuned to have a similar width to the optimal localizations seen in the height localization, which we would expect because we've tuned it for assimilating a single observation of height. However, there's a much different width seen for the V self-correlation localization, and again for the cross covariances. So that's perhaps suggesting that maybe there could be an improvement made if we tuned a more complex Gaussian with different widths for each variable and for the cross covariances. It's also notable that there's a dip in the caused by the balanced nature in the optimal localizations for the cross covariances, which a Gaussian doesn't imply at all. So that could be a reason for the Gaussian to perform less well. It's difficult to compare the hybrid localization to the traditionally formed localizations because it's damping towards a mean and not towards 0. And so I'll show a second plot, which is a localized mean covariance, which shows that and in this case, you can see that the hybrid localization is essentially allowing more information through at every point. So finally, I can show some results. So these plots are showing the RMS error in the height and wind, and the RMS adiastrophic wind when assimilating a single observation of height into this regime. And it can be seen that for both the height and the wind, there's a decrease in the RMS error seen from using the Gauss and the OSTC, again from the OSTC to the OVTC. And finally, the hybrid localization is showing the lowest error. It's in particular, you can see that either side of the observation, there's quite a significant improvement in all of the optimal localizations compared to the Gaussian. Finally, when considering the adiastrophic wind introduced, the initial states were all perfectly balanced. So all of the adiastrophic winds, those results can be thought of as being due to the localization process. And it can be seen that the OSTC and OVTC are introducing significantly more balance than the Gaussian. The hybrid introduces less balance than the other optimal localizations, but in this case, still more imbalanced than the Gaussian. Now I'm showing a second case. We're simulating a single observation of wind, and we see similar results for the error in the height and the wind, with the hybrid performing the best and Gaussian the worst. But in this case, the adiastrophic wind is the least for the hybrid. It's even performing better than the Gaussian. So some conclusions. The optimal localizations have shown an improvement upon the a more traditional form of localization. That's the Gaussian localization. The optimal localization was performed the best in terms of giving the lowest RMS error. And it's been shown to introduce less balance than the optimal localization for the traditional form, dumping the covariances towards 0. The form of the optimal localization showed some features, such as a difference in the width for each variable and for the cross covariances, and also a dip in the center of the cross covariances that were not reflected in this choice of tuned Gaussian. And so finally, some future work. We're looking into applying more complex tuned forms of localization inspired by the optimal localizations. And finally, I'm working on a better model that's based on states that are a combination of waveforms and not single waveforms here, which will have properties more similar to a realistic weather system. So thanks for listening. I'm happy to take any questions.
Okay, thank you, Rebecca. There are a couple of questions. One's being typed and one is already to go. So, actually, there's a third question coming in. Okay, so Lars asks, you show a zero localization weight for V to H localization. Does this mean that the two fields are locally not correlated?
Zero localization weight. Sorry, I'm not sure.
I mean, he's adding a correction. I mean at zero distance.
Yes, at zero distance. Because it's a feature of the balanced states that we use. There's always a zero because they're a sine and cos form. There's always a zero correlation at zero distance.
Cool. So Peter Yan has a question. Okay. Your results are fully wave-like. If you have many wavelengths, will you get back to a Gaussian?
Yeah. So these states are very unrealistic. The next model that's being developed at the moment is addressing that. I think perhaps if we had all the wavelengths with the same amplitude, maybe. But in our model, we're using power laws, sort of because of the expected distribution of the amplitudes in the atmosphere, in which case it doesn't, so far results aren't showing it turns into a Gaussian.
Okay. He says, okay, thanks. Now, Haristo asks, the new optimal localization functions exhibit non-Gaussian shapes. I wonder if the localized covariance remains positive semi-definite, which would be expected with the Gaspari cone functions. Further, how does the more complex shape impact the rank of your localized covariances?
Yeah. Sorry. Yeah, I haven't checked if they remain positive semi-definite, so I'm not sure about that. Perhaps that's probably worth checking. I think I'm quite certain that it will increase the rank of the localized covariance matrix. The good points that I'm aware of, I haven't specifically looked at yet, but maybe I will do.
Okay, we've got time for there's one more question here that I'm going to ask, and then we'll move on. Chris Snyder asks, can you clarify what is being optimized in the full, in brackets, many dimensions case? Is it covariance matrix or the gain?
Optimizing the gain, but there's this decision made to apply. It's perhaps not specifically. It's only optimized. The gain is optimized in a single observation case, and there's a perhaps step away from optimality because we were applying it in the covariance matrix.
Okay, are there any other questions? I'm just looking here.
So Steve, just the add-on from my side. So if there are more questions, just type them online and Rebecca can answer them later on also in written form.
Yeah.
Okay, I think, well, thank you again, Rebecca, for a